Well, we talked about the Laplace transform, finding Laplace transforms, finding inverse Laplace transforms. What do we do with these guys? Well, here's a property that's going to help do something pretty important: solve differential equations. What's the Laplace transform of the derivative of a function? Well, if we go back to the definition, it means take this integral. And we'll take this integral by integration by parts. Call this e to the minus st, the u part, and this f prime dt, the dv part. So by integration by parts, that becomes this. Here we can pull the s out. I'll actually pull the minus s out. We have a plus s at part. And here you should already recognize this is the Laplace transform of the original function f. And here we have to evaluate between the two limits. It means these two limits. Easy one is where this t goes to 0. In fact, 0 from the left, that's what the little minus sign means. It's just the function evaluated at 0, or the limit at 0 from the left. Way we define the Laplace transform. And this guy, as t goes to infinity, if the original f function had a Laplace transform, it should be true, that this is 0. So you're left with the Laplace transform of the derivative of a function is s times the Laplace transform of the function minus this initial condition. I think we assumed here it was continuous. If it's piecewise continuous, you have to break it up. But anyway, here's the basic relationship. And you could keep doing that. And in fact, what you get, this bottom line here might be what would be in your table of Laplace transform properties in pairs. The nth derivative, the time domain or the t domain, means multiplying by s to the n in the Laplace domain. And then you have to subtract off these initial conditions. The power of s goes down as the derivative goes up. Kind of memorize that, or just look at this kind of these formulas in a table or something when you do these problems. So now we can solve differential equations. And I like step by step. In fact, I call my method the SAIL method. Let's say this is the problem we're asked to solve. Here's the differential equation and the initial conditions. The first step is write the subsidiary equation, which means take the Laplace transform term by term of this equation. So from what we just learned about transforms, the Laplace transform of this guy, y double prime, is going to be s squared times big Y minus s times y0, which is 1, or minus s, then minus y prime, which is 3. Minus 2. And I would put this part in brackets or parentheses. A lot of times the sloppy-eared students often make is to fail to distribute this coefficient. So it's minus 2 times what's the Laplace transform of the derivative, the first derivative. S times big Y minus y0, which is 1, plus 5 big Y. So this right here is the subsidiary equation. Just stop right there. That is your subsidiary equation. Don't start doing algebra yet. That's the next step. So the next step is to start doing some algebra on this, because we want to isolate y on the left side, this big Y. So we can gather up all the big Y terms. S squared minus 2s plus 5. Big Y, minus s, a minus 3, and a plus 2. Let's see. Bring these guys to the right side. You'll have plus S plus 1. And then divide by this out here. And we've now isolated big Y sub S, or the Laplace transform of the solution. So all we need to do now is take the inverse Laplace transform of this. I'm going to say it's a good idea to get Y all alone on the left and a ratio of polynomials on the right. And in this case, we're going to use that. This denominator has complex conjugate roots. So we'll use that to complete the square method for the inverse Laplace. I'm going to need a S minus 1 squared. That will give me S squared minus 2S plus 1. I need to add another 4 to get to 5. And I want the S term, the term that matches this S minus 1. The S minus 1, then I have to add 2 to make this come out right. Split those two things up. And these things, without further ado, are in the Laplace table. This is e to the t cosine of 2t. And this is e to the t sine of 2t. There is our answer. The Sale method. I'll do one more example of a Sale method. Here's just a first order equation, but it has a non-zero term on the right. So first order, so we only need one initial condition. Subsidiary equation. Whoops, what happened there? What happened there? This will be S times big Y minus that 2 plus 6 big Y. And the Laplace transform of e to the 4t is 1 over S minus 4. You have to look that up in the table if you're not familiar with some of these common transforms. That's the subsidiary equation. Now we start doing algebra. We'll get all the big Y stuff together. I'll have an S plus 6 equals this on the right plus a 2, which I bring this over to the right side. Get that over in a polynomial over a polynomial. Divide through by the S plus 6. There is my Y on the right side. Polynomial over a polynomial in this. Now we do the inverse Laplace transform. We have to do some partial fraction expansion in this case. Let's see, what is A? Cover up the S minus 4 and evaluate the rest at plus 4. This will be 8 minus 7, which is 1. 4 plus 6 is 10. And the B, cover up the S plus 6 and evaluate the rest at, typo, this 2 should be an S. Evaluate the rest at minus 6. So we have minus 12 minus 7, which is minus 19. Minus 6 minus 4, which is minus 10, or 19 over 10. These are easy inverse transforms. This is e to the 4t, this is e to the minus 60. Here is our solution. Way to solve ordinary differential equations that are linear.